Okay, for the sixth review, the first thing we're going to do is graph each log function. And so for logs, you need to remember that their inverse is exponential. And with inverses, we always switch x and y. So for this right here, our parent graph is just going to be the graph before transformations. So it's just going to be log base 3 of x. Okay, so the transformations are left 1 and down 2. We can fill out everything because we know the pattern of logarithms. The equation of the asymptote is going to be x equals -1. When it was exponentials, it was y equals, but because we switch x and y with inverses, this is why it's switching to x equals. Same with domain and range. This is going to be x such that x is greater than -1. And the range is going to be y such that y is an element of the real numbers. Okay, so we can get all that information. You can also just get it from the graph. So if we make a table, the difference with logarithms is that we are going to put those standard 5 inputs into the y. And what we did is we did 3y equals x and plugged in, or you just memorize that because the base is 3, this is going to be 1/9, 1/3, 1, 3, and 9. So you're going to plot those initial points. So 1/9 -2, 1/3 -1, 1, 0, 3, 1, and then 9, 2 is off the graph. You do kind of want to keep an idea of how it's curving, right? So you don't want to not put it on there, but you can go without transforming it. And then we're just going to move every point left 1 down 2 because I don't like to go past my asymptote on accident. And since I already know it's at -1, I like to plot that first. And then every point we're going to go left 1 down 2, left 1 down 2, left 1 down 2, left 1 down 2. And then we know it kind of does that smooth curve and it coasts along its asymptotes with arrows on both ends. It's going to get closer and closer to that asymptote, and it's going to go higher and higher. Okay, so that's the typical shape of a logarithm. Next one, we are graphing the natural log of x plus 2. So again, if you don't know what your parent graph is, it's always the graph before you do any transformations. So take care of your transformations. You're pretty good at noticing that that's going to be left 2 because the 2 is in with the x is horizontal, and when it's in with the x, it's the opposite. So the parent graph is just the natural log of x. The equation of the asymptote is always going to deal with the horizontal shift. So this is going to be x equals -2. And because of the asymptote being at x equals -2, the domain is going to be greater than -2. And the range for all logarithms is always all real numbers. Then we make our table. And again, for our table, we are putting those standard 5 inputs in the y, and we're converting our parent graph into exponential form, which would be e to the y equals x. And so that's going to be 0.1, 0.41, 2.7, and 7.4. Plot those points first, and then we're going to move everything left 2. So again, I like to put my asymptote in first so that I don't accidentally go further than I should. And this is nice because everything is just going left 2, left 2, left 2, left 2, and left 2. And oh, that's hard to see. I'll do it in the other color. So left 2, and there is our graph. Okay, let's do the last graphing one. Another natural log graph. Transformations are going to be reflect over x-axis. Don't forget to put that x-axis. Reflect is not enough. It's not specific enough because there's lots of reflections in math. We're going to move it up 3. The parent graph, if I take away those transformations, is just the natural log of x. The equation of the asymptote, because I didn't move it left or right at all, it's going to stay at the standard place, which is x equals 0. And then even though I'm doing a reflection in the x-axis, it's not going to change the sign on my domain because I'm still going to be to the right of that asymptote, so that's going to be greater than. Now we'll see it in the graph, so if you're not sure, the graph and the algebra should always be consistent. One shouldn't be different than the other. So again, we are putting, whenever we do logarithms, it just makes our life easier for plugging in to do the points in the y. So that's why we're going to do that. Again, got to have those e to the x values memorized, which is the parent points for the natural number e. Then what I have to do is take care of that reflection. We've been taking care of reflections and either stretches or compressions in the table because it just makes our life easier. And then we do shifts in the actual graph. So this is going to be 2, 1, 0, 1, 2. So I'm going to plot those, and then the last thing I have to do is move those all up 3. So 0.1, 2, 0.4, 1, 0, 1, 2.7, negative 1, and 7.4 will be at negative 2. So the graph went from being like this and then just reflecting. So since my asymptote is at x equals 0, going to draw that in. And then the last thing to do is move all these points up 3. And still taking that curve and still getting that arrow, but now it's going to go up along its asymptote instead of down. Okay, moving on. Make sure you read your directions here. These do not say evaluate or simplify. They are seeing if you know how to convert from a log form to exponential form. So you do not have to simplify. You do not have to do anything. This is just 5 to the negative 3 equals 1 over 125. Natural log of 1 is log base e of 1. ln is shorthand for 4 letters, log and then a subscript e, so make sure you're aware of that. So this is just going to be e to the 0 equals 1. And then if there's no log written, it's base 10, so this is 10 to the first power equals 10. The next one says to rewrite the equation in log form. So we're going the other way. So if it's in log form, it should probably start with the word log. Whatever the base of the exponential is the base of the logarithm. And then logs are exponents. So the exponent becomes the 2. That leaves 36 to be the argument. So it still has that round pattern of the order you put your numbers in. So this is log base 1/4 of 16 equals negative 2. And this one is log base e of 7.4 is approximately 2, but we don't ever leave log base e. So that's the natural log of 7.4 is approximately 2. Number 4 is just making sure that you really hit home and understand that logs and exponentials are inverses of each other, just like square roots and squares, addition and subtraction. So the inverse of this is a logarithm with the same base, and the inverse of a logarithm is an exponential with that same base. Okay, moving on to the next part. This says evaluate the logarithm without a calculator. So you can see that these all have numbers with them and not variables. So that means we can simplify if possible. The way we do this is 5 to what power is 25. This equals 2. 1/2 to what power equals 1/8. So a lot of students think that this one right here is actually going to be -3, but it's not, because these are both reciprocal powers. So this only 2 to what exponent equals 8, that's going to be 3. Let's see, 1/3 to what power is 27. So the first thing we notice is that we do have one of the bases in the denominator, so that automatically means it's going to be negative. And then 3 to 27 would be 3 to the 3rd power, so that's -3. This one is saying 4 to what power equals -8. Hopefully you didn't even need to convert it to exponential. That's undefined. Think of the graph, the most basic logarithm. The graph asymptote is at x equals 0, so it has to be bigger than 0. It can't be negative and it can't be 0. This one, 64 to what power equals 8. So there's no reciprocal powers, meaning there's no denominators. But when we look at this one, we're looking at this being a bigger number than that. So if it was reversed, 8 to what power is 64, that would be 2. But because the 64 comes first, that means we would have to take the square root to get to 8. And the square root as an exponent is 1/2. Same thing with this one. 8 to what power is 2. No negative here because there's no denominator, but I'm trying to go from 8 to 2. If I was going from 2 to 8, it would be 3, but since it's 8 to 2, we're going to make that be 1/3. Alrighty, next one, 49 to what power is 1/7. So not only do we have it going in the denominator right here, which is going to mean that this is going to have a negative, but we also have that this is going from 49 to 7. So it's going down. So we're going to have a negative and a fraction. So because 49 to 7 would be a square root, it would be the -1/2 fraction. For this one right here, what you're going to want to remember is that because logarithms are inverses of exponentials, when you do order of operations, we do exponents before we would multiply by 4. So we're going to do the logarithm. So this is really saying log base e of e. So that's really saying e to what power is e? Well, this e is to the first power. So that means e to what power is e to the first power? That's just 1. And then when we multiply it by 4, we get 4. Same thing over here. This is saying log base e of e to the 10th. I know it sounds funny that I keep repeating this, but natural log is abbreviated for 4 letters. So natural log is 2 and it goes to 4. So I have double e's in this example. So this is saying e to what power is e to the 10th. It's not a trick question, it's just 10. The other thing that you might have saw is these are inverses of each other, natural log with base e and that, and so your answer is just the exponent. We can use that same technique here if we want. We can just say log base 11 and exponential base 11 are inverses, so they undo each other and we're just left with square root 3. If that is too hard to process, that's okay. Just translate it to the exponential and go from there. Okay, now we're getting into expanding. Just a friendly reminder that when you're expanding or condensing, you always need to look for those logarithms that have a single number rather than a variable, because sometimes they simplify. We forget about them because it's new to us, but we still have to be able to see them. So this one is going to be log base 3 of 5 plus 2 log base 3 of x. Because we're multiplying, that goes to addition, and the 2 is only on the x. That's why it's in front of the log base 3 of just x. For the next one, we have 1, 2, 3 terms, so we expand. We should have 3 logarithms. Oops, I forgot to put my exponent in front. Okay, next one, the log without the base is actually log base 10. So this is log base 10 of 8 minus, and it's minus because the y to the 4th is in the denominator. So that's going to be 4 log y. Moving on. This one, we get log base 4 of 2 plus log base 4 of x minus log base 4 of 7 minus log, oops, forgot the 2 again, 2, because this has an exponent of 2 log base 4 of y. But this is not the final answer. I need to go look at the parts that have single logarithms with numerical values. So this is saying 4 to what power is 2. And because I'm going big to small without any denominators, I know this is going to be 1/2. So that can be evaluated. Log base 4 of 7, 4 and 7 aren't related exponentially, so I cannot simplify that one. Okay, moving on to the next one. Again, write small on these because you're going to want 2 lines. The square root, anything under a square root, this is a square root and it's to the first power. So this is going to be 1/2 log 11 plus 1/2 log x plus 1/2, but then there's a 2 here, so it's going to bring the 2 out in front, and that's going to be log y, and then minus 3 log z. And I just want to point out real quick that this z cubed is not under the square root, and that's why there's not a 1/2 in front of it. So we just need to clean this up a little bit. 1/2 log 11 plus 1/2 log x. Also, I'm checking to see if any of these number ones can be simplified. So I am still looking at this. This is a logarithm with base 10, so it's not related to 11 exponentially. This right here, some students still have a hard time with that. 1/2 times 2. This is really just going to say what's half of 2, which is 1. So this just simplifies to log of y minus 3 log z. Ooh, 2 z's. That was weird. Okay, last expanding is going to be right here. And because this is to a 4th root, everything's going to be to the 1/4. So I get 1/4 natural log of 3 plus 1/4. And then I have a 2, so that means times 2 natural log of y. And then again, just for friendly reminder purposes, multiplying fractions, no big problem. Top times top over bottom times bottom. So this is 2/4, which you know reduces to 1/2. So this is 1/4 natural log of 3 plus 1/2 natural log of y. Okay. So again, just some tricky exponent math. They're both there. You just multiply them because that's the property. 7 asks us to condense all of these. So in order to condense the logarithm, we need to go back the other way. So that means that there's only going to be one log. So this is going to be log base b, and then 4. And because this is addition, it means multiplying. And we only write one logarithm. So I have log base b of 4 times x times y cubed. B is a little tricky. There's lots of ways to approach it, so you can take your approach that you want. Here's what I'm going to do. I'm noticing right away that I can simplify log base 3 of 9, which is saying 3 to what power is 9? And that is 2, because 3 squared is 9, minus, and then I have the 1/3, and just like the last one, I also see log base 3 of 27, which is 3 to what power is 27, and that's 3. So doing fraction math, I get 1 times 2 over 2 times 1 just simplifies to 1. And then 1/3 times 3 also simplifies to 1, so this just comes out to 0. If you wanted to actually condense first, the other way that you could do this, which is always good to see because you don't know what you're actually going to feel like doing, is you would go log base 3 of 9 to the 1/2 divided by 27 to the 1/3. Because this 1/2 comes up, minus is division, the 1/3 comes up, and we only write the logarithm once. So then we would simplify. That's going to be log base 3 of 9 to the 1/2 is 3, 27 to the 1/3 is 3. So that's log base 3 of 1, which is 3 to what power equals 1, and that's 0. So there's two different ways. There was a shorter way, but depending on what mode your brain is in, you might have done the other way. Okay, this one we have natural log of 12 divided by x squared because this is divided. 2 goes up, only write the natural log once. This one is natural log of 7 times 2 to the 3rd divided by, make sure this is in the argument, x, and then we learned the lesson that if it's a minus, it always goes in the denominator, so I know it seems like there's 2 dividing, but it's not, and then we just clean that up. 2 to the 3rd is 8, and 7 times 8 is 56, so we get that. For part E, same stuff. We're just condensing a bunch. 3 comes up here. This becomes divide. Only one logarithm. And then this goes back to multiply, but we also learned that that just means it goes in the numerator. So when all is said and done, I get the natural log of x cubed divided by y, and then times z to the 1/2, which is the square root of z. All right, let's go to the back side where we're practicing the last 2 sections for this unit. Question 8 is actually really interesting and a good multiple choice question. It says, which of the following is not equivalent? So the first thing that we know is that if we were to use the properties, the first property would say that because we're multiplying, we need to add them. So this right here is a property that works, and we're looking for ones that don't. Okay, so that one works. Then what you may not think to do, but that is pretty necessary for these problems is to notice that they changed the base in this answer. So these are both base 10. When they change the base, you should try the change of base property. So if I were doing the change of base property on this guy, it would be the log of 3a. So that's log base 10. And then, so the argument goes in the numerator and the base goes in the denominator with the new base because it's called the change of base. So how did I know to even look at that? Because the logarithm in the original problem is m and the logarithm in this answer is not. And so I said, well, let me try that change of base property. Okay. Then I'm looking at this one and I'm like, okay, what I could do on this one is it already has the change of base property. The only thing I could do is bring this m down in front, but that's still not the same thing in any way, shape, or form as that. So I'm thinking that might be my answer, but I'm going to go ahead and try and condense this here just to make sure. So to condense this, this is going to be log of m, log base m of a squared times 9 to the 1/2 all over a, because this is dividing, so it should be on the bottom. So that's log of m of a squared, and a simplify to just a, and 9 to the 1/2 is 3. So that is going to simplify to 3a, which is what they gave me. So perfect. That is the one that is not equivalent. Good test problem right there. Okay, now we're solving equations. So we're going to be going back and forth between exponentials and logs. So we just have to take our time. So the first one is 2 to the x equals 22. And 22 is not related to 2 exponentially. So the way undo a base of 2 is with a logarithm of 2. So log base 2 of 2 to the x equals log base 2 of 22. Then the log base 2 of 2 are inverses, so they cancel each other out on the left side, but they don't cancel each other out on the right side. So that is our non-calculator answer. And then if we need our calculator, I don't know if it works in this one. So let's see, you hit math, and then there's log base. Enter, and then that was log base 2 of 22. Enter, round to the 1,000th, so 3 decimal places, and then we have our answer. Okay, so x is approximately 4.459. Okay, next one. This is the one where I really wanted everyone to know that never ever will you exponentiate 3 times. That's improper, okay? You will only exponentiate twice. What you do to one side, you do to the other, okay? So I'm going to erase that. So what we're doing is we are going to condense this using our properties. So this is log base 3 of x times x plus 8 equals 2, okay? And I don't know why I wrote 2, 2, 2 instead of 3, 3, 3, but I'm not going back to re-record that, okay? So this is 3 and this is 3. You will only exponentiate twice. What I'm actually doing is I am taking that logarithm and the other side and putting it in the exponent. So I'm going to write it just one time to show you what it looks like. Okay, so then these are going to undo each other, and then I'm going to get x squared plus 8x when I distribute equals 3 to the 2nd power, which is 9. I'm going to subtract 9. and I get x squared plus 8x minus 9 equals 0. Then I'm going to t-chart x plus 9, x minus 1, and then that gives me x equals negative 9 and 1. Because this is a logarithmic equation, the original equation is with logarithm, I have to check to make sure the arguments aren't negative. So when I take negative 9 and I plug it in to this x right here, it does make it negative, and then it's already not an answer, but just so you can see, it also makes that argument negative. Now I want to work on plugging 1. 1 does not make them negative, so this is an extraneous solution, and my final answer is just x equals 1. And I don't need to have an approximate because it's an exact solution no matter what. Okay, for this one, I do have an exponential, but I'm noticing that both bases here, 27 and 3, can be written in the same way. So this 27 can be written as 3 to the third, and then this is already got a base of 3. I'm going to multiply those together, so I get 3 to the 3x equals 3 to the 2x plus 3. And now that they both have a base of 3, I'm going to take a logarithm of both sides. And that logarithm is going to undo the exponentials, and I'm just left with 3x equals 2x plus 3. Do the math on that. And I get x equals 3. I do not need to check for extraneous solutions because the original problem is an exponential, not a logarithm. Okay, D, I don't need to condense first because they're not both logarithms. One's a single value and one's a logarithm. So my first step is to isolate the logarithm. So I end up with log base 3 of x minus 3 equals 2. How do I undo a log? I exponentiate, meaning I put the equation into the exponent. That means these are going to cancel, and I'm left with x minus 3 equals 9. So then I'm just going to add that 9 or add that 3 to the other side, and I get x equals 12. Again, only an exact solution. Next one is an exponential, so isolate the base. So I get 3 to the x equals 18. 3 and 18 are related by multiplying, but this is an exponential. They're not related by exponents. So to undo the exponential with base 3, I take a logarithm with base 3, and I get x equals log base 3 of 18. And then I'm going to plug that into the calculator, and I get 2.631. Okay, moving on. F is a logarithm, and there are 2 logarithms. Again, we would never go like this. I just wrote 3 bases of 4s. We would never do that. The max you're going to write is 2. So you need to make sure you condense first. So I'm going to make this multiplication, and I get log base 4 of x minus 3 times x minus 4 equals 1/2. Now you'll see that I'm only writing it twice. These undo each other, and I get x squared minus 7x plus 12 equals 2. I FOILed this, and then 4 to the 1/2 is like the square root of 4, so that's how I got 2. Subtract 2 from both sides. X squared minus 7x plus 10 equals 0. T-chart. And I get x equals 5 and 2. Before I can deem those correct answers. I need to plug them into the arguments. So I am looking here. When I plug in 5 minus 3 is 2, and 5 minus 4 is positive 1. So that one works. However, when I plug in the 2, this 2 here into this guy, 2 minus 3 is negative 1. So that's not a good solution. It's just x equals 5. Okay, moving on. Again, this is a type of exponential where we can look at the bases of 8 and 1/2 and see that they're related by the base of 2. So this is 2 to the 3rd power, and this is 2 to the negative 1. And then what we're going to do is make sure we multiply those. So we get 2 to the 3x minus 3 equals 2 to the negative 2x plus 1. Now that we have the same base, we can undo the base by taking the logarithm so that we can actually figure out what x equals. And so then from there, we're just going to get the variable on one side, and that is going to be 5x equals 4, and then we're going to divide by 5, and get x equals 4/5. Again, no need to check to see if this is an extraneous solution because the original problem is exponential, and the domain of an exponential is all real numbers. Moving on to this logarithm, we are always going to condense first. So this is the natural log of x times 2x minus 1 equals 0. Then I'm going to exponentiate with the same base. These are going to undo each other. And then e to the 0 power is 1 because anything to the 0 power is 1. Then I have 2x squared minus x minus 1 equals 0. T-chart. And I get x equals negative 1/2 and 1. And then just like always, because the original problem is a logarithm, I'm going to take this and plug it in there. And I don't even want to do that math, but I can see that if I plug it into the second logarithm, it's going to be negative, so it's not going to work out. So negative 1/2 isn't going to work. When I plug in 1, it does work. So the only solution to that is x equals 1. This one right here, we have to remember that if the base isn't written, it's a 10, and the logarithm is isolated. So this is a little bit of an easier one. So I'm just going to exponentiate both of those, and that's going to undo the log of base 10. And then I just have to make sure I do 10 to the 4th power. Just so you know, whatever the exponent is with tens, that's the number of zeros that you have. So it's not like you actually have to multiply those out. And then I'm going to add 2 to both sides, and I get x equals 10,002. And then I will check my answer, but clearly that argument is still going to be positive, so I don't have to worry about it. Okay, moving on to J. Always isolate your exponential before you do anything else or your logarithm. So that's going to equal 19. Then I'm going to multiply both sides by 2 to reverse that fraction. And then now that the base and the exponent are isolated, I'm going to do the inverse and take a log of base 10. You don't have to write base 10, and you shouldn't in your final answer. We get x plus 6 equals log of 38. I'm going to put that in parentheses so I don't actually accidentally try and subtract the 6 from the argument when it doesn't belong in there. So that right there is the exact answer. And then when I plug that into the calculator, I get negative 4.420. Okay, k is another exponential. So isolate that base. Okay, so we get 3e to the 3x equals 2. divide by 3, divide by 3, e to the 3x equals 2/3. How do I undo an e exponential with a natural log? Then I'm going to get 3x equals the natural log of 2/3. And then again, am I done? No, because you're asked to solve for x. So you need to get the x by itself or isolate the x. And then that is what it looks like in the exact form. And then when you type that into your calculator, you get the approximation of negative 0.135. Next one is L. The logarithms are isolated on each side, so we can jump straight into exponentiating, which means those are going to cancel out. And I get 3x minus 3 equals x minus 6. Get the variable on one side and the constant on the other side. And that gives me 2x equals negative 3. So that means that x equals negative 3 over 2. And then because this is a logarithm, I would need to check it. I didn't want to deal with fractions to check it, so I was like, I'm just going to see what happens if I think of it as negative 1.5. And if I take negative 1.5 and plug it into that x, it's going to be negative 7.5, which means that negative 3/2, or which is the same thing as negative 1.5, doesn't work. So this logarithm actually has no solution. All right, M. So you're going to isolate the logarithm first. It's already done because the logarithm's on one side. So the first step is going to be to exponentiate. So those are undone. I get 6x minus 5 squared equals e to the 4th. So you could try and FOIL that out and go from there. But sometimes we just need to recognize that we can just square root if it's a perfect square. So we get 6x minus 5 equals plus or minus e squared. It's plus or minus because we drew in the square root. Then we're going to add 5 to both sides. Whenever I have that plus or minus in a statement, I like to put the number in front. It just looks more friendly to me. And then divide by 6, divide by 6. So our non-calculator answer, there's actually 2. 5 plus or minus e squared over 6. We did start with the logarithm, so we would need to plug them in, except for our knowledge about squares. No matter if I do get a negative in the parentheses, it's going to be squared, which is going to make it positive. So I don't actually have to try and figure out what this is and plug it in, but I do need the approximations. So just keep in mind, to plug into your calculator, you're going to have to plug in twice. You're going to have to plug in the positive e squared and the minus e squared, and then you're going to get 2.065 and negative 0.398. And then moving on, this one looks interesting. All right, first thing I'm going to do is subtract 6. Then I'm going to divide by 5. Then I'm going to exponentiate. Be really careful here because sometimes students are tempted to say 3 times 3, but that's 3 to the 3rd power, so that's 27. Because the highest power of x is greater than 1, we are going to get one side equal to 0 then t-chart, oops. So I get x equals 9 and negative 3. And again, I just got to go to the argument of that logarithm right here and make sure when I do the math in there, it's not going to give me a negative. So when I plug in 9, I'm going to get 81 minus 54, which is positive. When I plug in negative 3, negative 3 squared is what? 9. And what's negative 6 times negative 3? 18, also positive. So both of those are good. Last one. Again, you're only going to ever exponentiate twice. So you wouldn't go 4, 4, 4. Never ever would you do that 3 times. You always got to condense first properly. So this is log base 4 of x times x plus 12 equals 3. And then we're going to exponentiate. And then we get x squared plus 12x equals 64. And then we are going to t-chart that. Ooh. 16, x plus 16 and x minus 4. So we get x equals negative 16 and 4. Automatically, because of that being just an x, the negative 16 is disqualified from being a solution. It is extraneous. And that is it.